to the second lecture on ECD. In this lecture, we'll study Miller's theorem. In last lecture, lecture number 1, we studied that BJT transistor has two junction capacitances. One capacitance is between the input terminal and the common terminal emitter. It is also called the input capacitance, and CBC. This is the capacitance between the output terminal, the collector, and the input terminal, the base. And we also studied a common emitter based amplifier in our last lecture, and we studied few basic things about the frequency response. In this lecture, we will study how to segregate this one, how to divide this CBC into two parts, such that one of those parts is solely at the input and the other is at the output. Right now, this capacitance is between the output and the input terminals. So we are going to divide this in such a way that one of the two parts that we are going to form is between the input terminal and ground, and the other is between the output terminal and ground. So let's see how to break this up. Miller was the first person to propose this division. This is our amplifier, a common emitter based amplifier, and this is CBC. The output terminal is, of course, collector, and the input terminal is base. Therefore, this capacitance is called CBC, the capacitance between the collector and the base terminals. So let's see how can we divide this CBC into two parts. Miller proved that the CBC can be broken down in such a way that this much CBC times AB plus 1 is the capacitance at the input side, and CBC times AB, where AB is the voltage gain, AB plus 1 over AB on the output side. Let's see how. Given this circuit that we have an amplifier and a capacitance CBC that is connected between the output and the input terminals. Let's see what the current is, the input current II. If II is flowing from VI to VO, so this is one node, this is the other node, the input node and the output node. And if we assume current to be flowing from input to output, this means VI is larger. So we can write a Kirchhoff's current law equation for this node. That is, I is VI minus V out, the net voltage drop across this impedance or capacitive reactance, divided by its reactance, XCBC. So this is very simple from circuit analysis. And we also know that the output voltage is minus AV times VI. The output voltage is the input voltage times the voltage gain, and there is a negative sign because CE, common emitter. The CE stands for common emitter. Common emitter amplifier is an inverting amplifier. It is an inverting amplifier, so the output is always inverted, or it is 180 degrees out of phase compared to the input. Therefore, I put a negative sign here. So let's plug this value V out here in this equation right here, and let's see if we put it here and solve. This comes out to be VI plus, and we can take VI common. This 1 plus AV divided by, or we can divide this IE here, right here, and take everything else on the left hand side. So VI divided by II is XCBC over 1 plus AV. So this VI over II is, of course, the input impedance, the input voltage, divided by the current flowing into the input terminal of the amplifier. This voltage divided by this current, the current flowing into the amplifier. So the ratio of these would be the input impedance of the amplifier, ZI. ZI can be written as XCBC over 1 plus AV. This XCB, we know that XC, the capacitive reactance, is 1 over J omega C. So if we replace this XCBC with 1 over j omega CBC. This 1 plus AV multiplies with CBC. This means the Zi is the capacitive reactance that is equal to, or an impedance that is equal to 1 over j omega times this much capacitance. So now we have the capacitance CBC times 1 plus AV. This is what Miller told, that the portion of CBC that is visible at the input is 1 plus AV times the value of the capacitance CBC. And finally, what is the portion that is visible at the output? Miller told that is, what did he tell? He told that it is CBC times AV plus 1 over AV, and we are going to see how. Right, what is Z out then? If I out is the current flowing from V out to V in, this means this terminal, this node will assume the voltage of this node, the output node, to be higher, the voltage of this node to be higher than the voltage of this node. So therefore the current I out would be V out minus VI divided by XCBC. Solving in the same way, V out is minus AV times VI, or we can write this in terms of VI. VI is minus V out over AV. So putting everything and doing the same trick, dividing V out by I out, it comes out to be this much. So, and of course, V out over I out is Z out. So Z out can be written as XCBC is replaced with 1 over j omega CBC. So this comes out to be the capacitance that we are seeing at the output is CBC times this ratio, AV plus 1 over AV. So this is what Miller told, that if we break the CBC to the input and output side, the portion that is visible at the output side is this much, CBC times this ratio. Luckily, this ratio is around 1 because AV plus 1 over AV produces a result that is very close to 1. So the CBC remains almost the same at the output as it is, but on the input side, it is multiplied by a very large quantity, AV plus 1. It's a huge quantity. So CBC, the portion of CBC that is visible at the input is very large, whereas the portion that is visible at the output is approximately the same as it is CBC, because this ratio is approximately equal to 1. Right, that's all for this lecture. And in the next lecture, we will study decibel, because before we start studying the response of amplifiers at very low and very high frequencies. Thank you.